Okay, so welcome back to another video. Today's video we have an improper integral where our integrand is consisting of a combination of hyperbolic functions. So we have our integrand is from the hyperbolic tangent of x divided by 2 divided by the hyperbolic cosine of x dx from our bounds from 0 to infinity. So looks like a lot going on with, hyperbolic functions, but actually it just comes with some u-substitutions and some of the identities referring to the hyperbolic functions that you just substitute. And then it's actually pretty simple to actually integrate from there. So today's video is actually not that hard. It's pretty easy from a glance if you know your properties. So today is going to be a short video on this case. So some u-substitutions, some properties we're going to be using for the hyperbolic functions to substitute, and then the final integral before we get to that value is actually a simple integral to integrate from there. So with that out of the way, let's actually just jump right in. So for our u-sub, we'll let u equals x divided by 2. So now integrating this in respect to u and x, so we have that du is going to equal to just 1/2 divided by dx. And of course, we'll have to substitute this back in, so let's actually put in for by itself. So I have instead 2 du is then just equal to simply just dx. So with that, we can actually now go back and fill in our substitution. If I plug in 0, so that means that's still going to be 0. If I plug in infinity, then that's still going to be infinity. So thankfully nothing has changed over here. So now we have our hyperbolic tangent. So first we have is hyperbolic tangent of u, and then all this divided by, so let's see, I have the hyperbolic cosine. So I have an x, so if I just solve for x by itself, so that means I just get 2u, so 2u, and then multiply by our differential substitution, so times 2 and then du. So in other words, we can actually put this nicely to say that this is going to be 2 times the integral from 0 to infinity. Now what I can do here is that for the hyperbolic tangent of u, we can actually use that nice property that that's the same thing written as the hyperbolic sine divided by the hyperbolic cosine. And so with that being said, so we have the hyperbolic sine of u and then divided by the hyperbolic cosine of u multiplied by the hyperbolic cosine of 2u and then du. So now continuing forward, where do we go from here? So now let's actually again do yet another u-sub. So why don't I actually change to a different variable? Let's actually call this t. And in this case, we're going to let t be the following. So we'll let t be the hyperbolic cosine of u. So what's that? And then if I differentiate both sides, so that means dt is equal to hyperbolic sine of u and then du. Just don't get that confused. You probably might be thinking because it's a trigonometric function, you would think that following that same pattern would apply here. So if I were to say cosine of u, its derivative is negative sine of u, that's not the case. So sometimes you can't utilize that pattern. You have to be careful on how you actually take your derivatives carefully. So with this out of the way, so now doing the substitution yet again, so going back here, so I have 2, then multiply by our integral. So if I substitute 0 back into here, yes, for 0, so that means I'm going to get positive 1. And then if I plug in infinity, so that's actually going to be infinity over here. And so with this, we have now just substitute this back in. So that means that just cancels out with just dt, and then divided by, so let's see, so we said hyperbolic cosine of u, so that means t, and then multiply, so this is hyperbolic cosine of 2u. We're actually going to use that nice identity to say that that's the same thing written. So first, in other words, this is the same thing written, so let me actually write this down. So this is 2 multiplied by the integral from 0 to infinity of hyperbolic sine of u, and then hyperbolic cosine of 2u, that's the same thing, so let's see, hyperbolic cosine of u, and then multiply, so this is the same thing written as 2, then hyperbolic cosine square of u subtract 1, and then du over here. So now with this being the case, so now we can actually substitute this back in, so that means this is going to be 2 times t square. I apologize if I actually missed that step. So minus 1, okay, and then we have our dt over here. So now to spice things up a bit, let's actually factor out a t square from over here. So doing so, I have 2 multiplied by the integral from 1 to infinity. So that means, so this is going to be dt right here. And then factor out the t square from over here. So that means it's going to be a t cubed, and then 2 subtract t to the power negative 2. Okay, so now let's actually get a little clever and actually fix this up a little bit. So I can write this as 2 And then, so let's see, our integral is going to be from 1 to infinity. I'm actually going to put this in the numerator. So that's the same thing written as t to the power -3. And then now divided by, so let's see, 2 minus t to the power -2, and then dt. Because if you notice, now let's do yet another u substitution. So we already used u again. So well, we went to u, we went to t. That's where we're at right now. So why don't we actually just go back and use u again? This is the second time, because why not? So let's see. If I let u, we're going to let this be the denominator over here. We'll let 2 and then minus t to the -2. And then du, so just apply the power rule. So it's a 0. And then just put that in the front. So that's going to be a +2. And then t, then subtract the 1 from the exponent. So t to the power -3, which is great since I can also move the 2 back inside if I want to. But that also gets rid of that as well. So taking it an extra step further. So with this being the case, so now we have our new integral. So the 2t -3 dt, that gets rid of that. So that means I just have a du on the top. And then so we let that be u, so du. And then what I can do here is, of course, let's change our bounds yet again. So if I plug in infinity back to over here, this is actually going to approach just 2. And if I plug in, what is it, 1 into here, so that's just going to approach 1. A simple derivative, it's a 1 over u du. We know that that's going to be the antiderivative of ln of u. And then we evaluate our bounds from 2 to negative, or 2 to 1, 1 to 2. So in other words, that's the same thing written as ln of 2, subtract ln of 1. ln of 1 is equal to 0, we know that. And so therefore, the final answer to this hyperbolic integrand is indeed just the natural log of 2. So kept it simple, and with all these elementary techniques over here, we utilized, a nice little property with the double angle of the hyperbolic function, and we did a bunch of, I think that's 1, 2, 3 u substitution techniques we have utilized, leading to just a simple answer just like that. So yeah, that's pretty cool if you ask me.